There's a rule out there that's so fundamental, so unbreakable. It governs everything from the biggest stars in the cosmos all the way down to the refrigerator in your kitchen. It's not just some abstract theory, it's the universe's ultimate law of energy accounting. So let's dive in and see how it works.
Here's our game plan. First, we'll get a handle on the rule itself. Then, we'll unpack a really key idea called internal energy. After that, we'll look at the super simple equation that ties it all together, see how it shows up in real-world tech, and finally, we'll actually put it to the test and do a little math.
Okay, first things first. We're talking about the absolute bedrock principle here. Before we get into all the ways energy can change and move around, we have to understand the most important thing about it. It's always conserved. This one idea is the foundation for, well, pretty much everything else.
And there it is, the big one, the first law of thermodynamics. It basically says that the total amount of energy in a closed system, like the entire universe, is constant. You just can't make it from nothing, and you can't make it disappear into thin air. The only thing you can do is transform it. Change it from chemical energy in a battery to light energy in your phone screen. It's all just one cosmic game of exchange. This, by the way, is exactly why perpetual motion machines are impossible. You can't ever get more energy out of something than you put into it. The books always have to balance.
So, if we're going to track all these energy transformations, we need a way to measure the total energy that's just hanging out inside a system. And that brings us to our next big idea, internal energy. So what is it really? Well, you can think of internal energy, and we usually just call it U, as the grand total of all the energy that's buzzing around inside whatever it is we're looking at. It's like the system's total energy bank account. And that bank account has two main components. First, you've got potential energy. This is the energy that's stored up in the chemical bonds between molecules. Imagine a bunch of tiny little rubber bands, all stretched and ready to snap. Then, you've got kinetic energy. That's the energy of motion. All those molecules zipping around, vibrating, and bumping into each other. So, it's the stored energy plus the movement energy, all added together. Okay, so we've got this idea of an energy bank account, but how do we track the deposits and withdrawals? Well, that's where a beautifully simple but incredibly powerful tool comes into play, the non-flow energy equation. It's perfect for closed systems. Just think of it like a sealed box where no stuff can get in or out. This equation is how we put the first law into practice.
The first piece of our puzzle is heat, which we call Q. This is any energy that crosses the boundary of our system because of a temperature difference. So if you put a pot of water on a stove, you're adding Q to the system. You're making a deposit. The other piece is work, or W. This is energy we transfer using a force. Think about using a piston to compress a gas in a cylinder. You're physically pushing on it, you're doing work on the system. That's another energy deposit. And these two things, heat and work, are really the only two ways you can change the energy in a closed system.
So, what happens when you add up all the heat you put in and all the work you did? Well, you get the total change, or gain, in the system's internal energy. We show that change in with a little triangle, delta. So it's delta U, simple as that. And there it is, the whole thing in one elegant package. Heat plus work equals the change in internal energy. Q plus W equals delta U. This is the universe's ultimate balance sheet. Every single joule of energy has to be accounted for. It's either coming in as heat, coming in as work, or it's changing the balance of that internal energy account. Okay, that's all great in theory, but so what? Why does this matter in the real world? Well, let's take a look at how this law is the secret sauce behind some incredible technology that we use every single day. Two perfect examples are the massive steam cycles in power plants that keep our lights on, and the refrigeration cycle that's keeping your lunch from going bad. Both of these are just incredibly clever applications of the first law, all about moving energy from one place to another to do something useful for us.
Now, for these things to work nonstop, they have to run in a cycle. They go through a bunch of steps, and then they end up right back where they started, ready to go again. And here's the kicker. If a system completes a full cycle, its internal energy has to be exactly the same as when it started, right? Nothing has fundamentally changed. That means the net change, delta U, is zero. So all the energy that went in as heat and work has to perfectly balance all the energy that went out.
All right, enough talk. I think the best way to really wrap your head around this is to actually see it work. So let's roll up our sleeves and solve a quick problem using our new favorite equation. Okay, here's the setup. We've got some kind of system. We pump in 2,500 joules of heat energy. At the very same time, we do 1,800 joules of work on it, maybe by squishing it. The big question is, what happened to its internal energy account?
First, let's just pull out the numbers we know. The heat we added to the system, our Q, is 2,500 joules. That's our first energy deposit.
And next, the work we did on the system, our W, is 1,800 joules. That's our second energy deposit. Now, all we have to do is grab our cosmic balance sheet, our equation. We know that the change in internal energy, delta U, is just the heat you add plus the work you do. So let's plug it in. 2,500 plus 1,800 gives us a grand total of 4,300 joules. That's the change in internal energy. Every single bit of energy we put into that system has been accounted for. It went straight into increasing the system's internal energy bank account. See? The law just works. And that brings us to one last big idea to chew on. The first law tells us energy is always conserved. It's always accounted for. But that opens up an even bigger question, doesn't it? If energy never really disappears and it only ever changes form, where is it all headed? What's the end game? Now that's something to think about.